Coloring maps. World maps usually color the territories of neighboring countries by different colors for obvious reasons. If two countries having a common border were the same color, the viewer of the map may overlook the border between them. This simple problem from everyday life gave rise to one of the most famous problems in mathematics. Take any map with the countries still uncolored and try to color the countries so that no two neighboring countries get the same color, using as few colors as possible. What is the smallest number of colors that will suffice no matter what the map looks like? From a graph theoretical point of view, all maps are planar graphs, so we need to find a proper coloring of the faces of a planar graph. By proper coloring, we mean the faces that have an edge in common must get different colors. Note that faces that only have vertices in common may get the same color. Also note that by duality, this is the same question as asking how many colors do we need to properly color the vertices of a planar graph. Indeed, a proper coloring of the faces of the planar graph G naturally defines a proper coloring of the vertices of G star and vice versa. When coloring the vertices of G star, the criterion to fulfill is, of course, that adjacent vertices get different colors. This question was probably asked first by Francis Guthrie in 1852 and got soon passed along to well-known mathematicians as A. De Morgan and A. Cauchy. A little bit of thinking yields that at least 4 colors are needed as K4 is planar. Trying several maps, one is led to the conjecture that 4 colors always suffice. This is the reason that this problem had been called the 4-color conjecture. For a warm-up, let us prove that 6 colors always suffice. We will use the dual vertex coloring form of the problem as it makes induction proof easier to describe. Proposition 12.14. The vertices of any planar graph can be properly colored with 6 colors. Proof. Induction on V, the number of vertices of the planar graph G. If V is equals to 1, then the statement is obviously true. Let us assume that we know that the statement is true for graphs with V minus 1 vertices. Let G have V vertices. Then we know from lemma 12.11 that G has a vertex A of degree at most 5. Remove A from G to get the graph G prime. By our induction hypothesis, G prime has a proper coloring with 6 colors. Take such a coloring of G prime, then color A with a color that is not the color of any of its at most 5 neighbors. This means by duality that all maps can be properly colored using 6 colors. The situation is significantly harder if we only want to use 5 colors. The result, however, is the same. Theorem 12.15. The vertices of any planar graph can be properly colored with 5 colors. Proof. Just as in proving the previous proposition, we use induction. The only case in which the previous proof does not work is when A has 5 neighbors and they are all of different colors. In this case, denote by 1, 2, 3, 4, and 5 the colors of the 5 neighbors, y1, y2, y3, y4, y5 of A as they follow clockwise. Let G prime be the graph obtained from G by removing A and all the edges adjacent to A. If G prime has a proper 5 coloring in which y1 and y3 are the same color, then we are done. If not, then any proper 5 coloring of G prime must contain a path from y1 to y3, along which the vertices are alternatingly colored 1 and 3. By similar argument, if y2 and y4 cannot be the same color, then any proper 5 coloring of G prime must contain a path from y2 to y4, along which the vertices are alternatingly colored 2 and 4. This, however, is a contradiction, as a path from y1 to y3 and a path from y2 to y4 must always intersect. See figure 12.4. Again, this means, by duality, that any map can be properly colored using 5 vertices. How about the big question that of 4 colors? The 4-color conjecture remained a conjecture until the 1970s. Then, Appel and Haken developed a strategy to use a computer to split the problem into several cases and to check the 4-colorable property in each case. When they started running the computer program, it was not sure that the computer would ever finish. It could have happened that the cases lead to subcases, which in turn lead to subcases of subcases, and never end. This did not happen, however. After 1,200 hours of running time and the verification of 1,800 cases, the computer returned the verdict: 4 colors suffice. Good that there were no power outages in Urbana, Illinois in those weeks. Therefore, we can now call this statement the 4-color theorem. The only problem with the proof of Appel and Haken is that we do not really learn from it why the statement is true. A more concise proof would certainly be very welcome.